Blackboard about 30 minutes ago. It's in the folder of week 15, which is this week. And so I'm going to go through these points one by one. But what I want to do today is, because we cannot go over every single lectures again for the past 4 or 5 weeks, my goal is to give you some high-level guidelines in terms of what topics will be covered. And also I want to help you to navigate the content so that you can find the information you need more efficiently. The final exam, as I mentioned last week, the final exam will be in the same format as the midterm exam. So that means we're gonna, you're gonna take the exam through Blackboard. The questions will be in different styles or formats, some multiple choices, and there are 2 kinds of multiple choices questions. And we have also short answer questions and true or false questions. So basically these 3 major categories of questions. The number of questions we had in the midterm, if I counted correctly, it's about 50 questions. And we had, I believe, 2 hours the exam time. I would like to keep the number of questions roughly the same as last time. So it will be about 50 questions plus minus. And the exam time will again be 2 hours because there are a few people that we need to have accommodation. So for most of you, the exam time will be 2 hours. Also, the exam will be open book. You can refer to the materials that you have access. That includes the textbook, which is a PDF file, and also all the lecture notes that you can download from Blackboard. So, which means that you can refer to these materials during exam time. But the purpose of the exam is not let you to look for information in a short 10-20 minutes from these different chapters and lecture notes. So what I would like to do today is to give you this list of topics that we covered after the midterm. And for each of the topics, I list in this document where you can find more information. There are 3 sources of information for the topics we covered in the past few weeks. One major thing is the major source is the textbook. For example, here, the first topic is embedded processors. And that topic was covered in week 8. And that topic corresponds to these chapters in the textbook. In particular, this embedded processors chapter, it has more than 2 sections, but I want to narrow down the scope. So you will need to only read through chapter 8.1 through chapter 8.2.1. And roughly there are 14 pages of contents. I'm listing these chapters or sections here is to help you to narrow down, but I still encourage you to read other sections beyond these listed sections. Although I don't want to hold myself that only to these chapters and without the possibility of going beyond that. But if you read these materials very well and you understand the content, chances are you do well in the exams. But I'm not saying that I may or may not have a question that go beyond these specified sections. If I do have those questions, though, those will not be the majority. The majority of the questions will be coming from these particular sections in the textbook, in addition to from other sources. Also, for these embedded processor section, I list here the other source of slides, and all the slides are posted on Blackboard, and I number them using a numerical number that represents the week, and also kind of a part number. So I have A, B, C, D. Sometimes only have one section, one part, so you don't see a letter after the number. Also, the other source is the video, the lecture. Okay, I'm having some internet issue here. You may okay, the question is, when is the final? I believe is next Wednesday, the same time as we have now. So from 6:30. So back to the videos. So the videos, I have completed the video generation for all the past 4 or 5 weeks, excluding the previous week, week 14, because week 14, the content we covered was the networking part, and the networking content is not going to be on the exam. So another question. Is the link to the Zoom meeting same as the link for lectures? Yes, so you use the same link to join the Zoom session next Wednesday. And also I would like to require you to turn your video camera on. So you are visible for me to me and my TA. Okay, so let me go to the Blackboard. Okay, so this is what we have on Blackboard. You might see a little bit different from what I see here, but you will have access to all the weeks, the contents for these 15 weeks under the home page. If you click this, you will find this list. You can basically ignore the weeks before week 7. So starting from week 8, this is what you will find in this folder of week 8. So the lecture notes, the PowerPoint slides in PDF format is available here. This part is for the embedded processors. And this lecture 8B, this is the part for the AVR processor, which I will talk about it at the very end. In this particular week, it contains links to the recorded lectures. This 8A is the lecture for the embedded processors. And this 8B is for the input and output AVR processor. And I will talk about this separately. So as you can see that for embedded processors, you will find the lecture notes here, and then the recorded lecture through this link. And you will find the same structure in other weeks, week 9, 10, 11, and 12. For the textbook, can you see my screen?
Yes.
So the textbook, I list in the document here. So for embedded processors, we will focus on chapter 8.1 through 8.2.1. So that is, so basically here we're going to focus on the types of processors, and that covers microcontroller, DSP processors, and graphics processors. And then for the parallelism, in the class, we talk about parallelism versus concurrency. So that's the other topic you want to get familiar with. Let me just go to this part. There are different types of embedded processors. The majority of them are microcontrollers and microprocessors, which consists of CPU in addition to other components. Some of them are on chip, some of them are off chip. And because in the embedded domain, energy consumption is often a concern. So these processors often has a sleep mode that can reduce power consumption to nanowatts. And in lecture, we spent some time talking about DSP processors, digital signal processing, because in many applications, they do require a bit of signal processing to process analog signals, and then using filters to get to the target signal or output. Instead of using an analog circuit, we can use DSP processors to process these signals, to do FFT, to do any other signal processing functions. So you can refer to the lecture where we give an example of DSP processor, talking about these structures, the adder accumulation, multiplication and accumulation unit in DSP processors. You can read this. It covers some very popular microcontrollers that have been utilized in many applications. Intel's 8051, Atmel's AVR processor, that's the one we use in the Arduino platform. ARM is definitely very popular, widely used architecture. You can ignore, well, I shouldn't use the word. You can spend little time on PLC. We didn't talk a lot about this. This is kind of a special type of processor. x86, you want to read this part. Basically gives you some background information about Intel's processors and the evolution from 8-bit processor to now 64-bit, and also Intel Atom as one type of embedded processor from Intel, but now it's discontinued, unfortunately. Some examples of DSP processors here. It's good to read it. This is an example that we talked about in class. This is the implementation of the FR filter example. You want to refer to the lecture notes and the videos to see how we come up with this design. Some pros and cons about this this kind of digital signal processing. We didn't talk about graphics processors. Here, you just read these 2 paragraphs. I think that will give you enough information about GPUs, which is also one kind of very powerful processor for heavy computation, especially in graphics and also nowadays in general purpose computing, especially machine learning, AI applications. Parallelism and concurrency. This is an important concept. I think you definitely need to read this section to find out the difference between these two and be able to relate to what you saw in early examples. And also here, what is the imperative language? And a program language that express a computation as a sequence of operation is called an imperative language. Most of the program language that we use are imperative languages. C is a good example. Now, if we want to write a concurrent program using C, we have to use some other helper libraries, such as a pthread library. A thread library will be able to help us build this concurrent execution model, on top of the imperative C language. And we later have a lot more discussions about threads when we talk about multitasking. So this is let's mention a little bit about multitasking here. We didn't talk about this pipeline, so you can spend less time on this. All right, so that's the first part, embedded processors. Any questions? All right, so next topic is the memory architecture. So memory architecture, we talked about this in week 9. So if you go to week 9, so you'll find the lecture notes here in PDF, and then this is the link to the recorded lecture. I didn't break this down into smaller pieces, so you probably find a 15 minutes lecture there. And this corresponding text chapter in the textbook is chapter 9. It's here. So we have 3 sections here in this chapter. I would like you to read all the contents, even though you see many sections and subsections, but if you count the pages, it's about 16 pages, 16, 17 pages. This chapter has a lot of the important concepts related to memory architecture, memory technologies. First, memory technology basically talks about how we can read or write the memory component and how these memory components are built. And RAM is random access memory, so you use this memory at runtime. It's the main memory, so to speak, that you have in your system. It consists of 2 major categories, SRAM and DRAM. SRAM and DRAM both are used quite often. SRAM is faster but smaller in size. DRAM has larger capacity but only holds data for a short of time. So DRAM has to be periodically refreshed to keep the content. And both of these memory will lose content if power is lost. So both are volatile. And for SRAM, it's used to store important data structures that will need shorter access time. DRAM is for the majority of data where you want to do buffering, processing, etc. See. In contrast to the volatile memory, we have non-volatile memory, where you can store data even when power is turned off. You can do this by using batteries, but many of these current non-volatile memory can retain information without even supplying power. For this type of memory, there are read-only or mask ROM. These are the memory component that you basically write once before you use it, and when you use it, you only read content from this ROM. EEPROM, by the way, the firmware is often stored in ROM because we don't expect to change them. EEPROM is electrically erasable program ROM, and that's used typically in the situation where you want to have a updatable or upgradable firmware. You can store the content, either instructions or data, in EEPROM and use it as read-only, and you only make it rewrite the content when you want to update that part of the instructional data. Flash memory, of course, is a non-volatile memory, and based on NOR or NAND flash components. There are some pros and cons between these two. You're going to just read it a little bit. And also disk memory are non-volatile. Okay, so first section was about the memory type, and then the second section is about memory hierarchy. Hierarchy is a big term. It basically refers to how we organize these different memory components as a part of the computing system. Typically, a relatively small amount of on-chip SRAM is used with a large amount of off-chip DRAM. And then further down, there will be disk drives and other non-volatile memory that you can store larger amount of data or information even when power is off. The application programmer may not be aware how much is the physical memory because they often work with virtual memory. Virtual memory makes easier for the programmer to work with the programming environment because it presents the programmer as a contiguous address space. Address space basically refers to a continuous address range, so from 0 to up to the max. And the operating systems and or the hardware provides address translation between the virtual memory and the physical memory, or the logical address to the physical location in the available memory technologies. There's a piece of hardware called the translation look-aside buffer, which helps speed up some of the address translation. And then the next thing is memory map. Memory map is defines how addresses get mapped to hardware. A 32-bit processor can address 2 to the power of 32 locations, that is 4 gigabytes. And the address width is typically matches the word width except for 8-bit processor. the the memory map, for example, you can see here. So this is a example memory map of an ARM processor. You can see that the whole memory space from 0 all the way to FFFF, FFFF. So this is 32-bit all ones. So the total address space is 4 gigabytes. And we can segment them into smaller ranges. And of course, they together make up the whole address space. The first segment you can see here, this is about half gigabytes. So from 0 to 1FFF, FFF. Then the next address is 200000000. So you have another half gigabytes here and half gigabytes. And for different processors, they may use different memory mapping, but you find out the style or the method of mapping is the same as this one, even though the exact address range will be, of course, different. This is to say that in this example, if you access addresses in this range, that access will come to this DRAM, which is the data memory. If you use another address that falls in this range, then the actual access will go to the external device that happened to be mapped in this range. Okay, so basically what we're saying here is, even though you have an address, doesn't mean that you are accessing a location in memory system. This could be accessing another device, could be IO device. It may not necessarily be a memory chip or component. It just depends on how you map the address range. Okay. Yeah, this here is an example. LM3S8962 is I believe is an ARM-based processor. It has this 64 kilobytes of SRAM. So that's here. Let's map this part. Yeah, you can use this diagram and read through this two paragraphs to try to understand this example. I think it's important to understand Harvard architecture and von Neumann architecture. I believe, so this is the Harvard architecture. There's another sidebar talking about von Neumann architecture. Let me see, where is it? I think we'll be able to see it. Harvard architecture named after the, this this Mark I computer. Basically what we're saying here is the Harvard architecture is where you have instructions, memory, and data memory separate memory space. In contrast, the von Neumann architecture has one common address space with instructions and data all in the same address space. Register files are the most the closest memory component to a CPU. It's on chip. It's integrated in the processor. Often the time it's a small space. You may have 16, 32 registers, and each of them could be 16-bit, 32-bit, or 64-bit. Depends on the data width of the processor. The number of registers in the processor is usually very small because it's hard, very costly to implement larger register files in the processor. Beyond the registers, the next level is the scratchpad or caches. Scratchpad is a small amount of memory, just temporarily to store data. It's on chip inside the processor, and you can use it to store a small amount of data for later computation purpose. But I think you need to spend more time to understand the caches because it's I would say, one of the most important innovations in processor industry. It's to take advantage of the temporal and spatial localities of the applications, which may access the same data for multiple times, and or may access a contiguous memory region in a shorter period of time. And that's why cache may benefit by reducing the memory access latency compared to architecture without cache. It'd be good to read through this, although I don't think we covered a lot in the lectures, but these are important to just know about memory management unit, logical address translation to physical address, and why do we need to do that? Okay, so the next important part is the cache organization. So from this page 247 to, I believe it's to here, 251. These 2-3 pages talks about this cache organization. Again, the purpose of cache is to have this fast on-chip memory to store data or instruction that are often accessed in a short period of time, or a small region or block that may contain instructions or data that will be accessed in a short period of time. Because if you can find these data in the cache, you don't have to go further down to issue a access to DRAM, which is further away from the processor. The access time is much longer. So that's the whole purpose of those cache. The way we access information in a cache is to use address. This address comes from the processor itself, because when a processor executes an instruction, if the instruction requires to access a memory operand, it will generate an address and use this address to access data from either cache or memory. If there's no cache, of course, it has to get data from the memory. Now, with the cache, what we can do is we will use parts of the address to find the corresponding location, whether I have already the data in the cache or not. So what it will do is, first, it will use the last B bits as the block offset. Essentially, each block here in the cache has 2 to the power of B bytes. So if this is 3, then this block will have 8 bytes. And if this is 16, then this block will have, actually 16 is too big. So if it is 5, this block will have 32 bytes, and so on. And then beyond that, we'll use S number of bits to find out which set we're gonna have to check if there's a block that we would like to access. If the block in that cache is what we want. This here we have S number of bits, so the number of set will be 2 to the power of S, this lowercase s. So this from 0, 1 up to capital S, this uppercase S, we basically have 2 to the power of this lowercase s, these many sets. So from these bits in this set index, we'll be able to go to the corresponding set. Then the next thing is we will need to check the tag that is stored with the block. This is the actual data. We're going to check the tag if this is equal to the tag from the address. Now things get a little bit tricky here. Depends on how many blocks you have in a set. We have direct mapped. In that case, we only have 1 block in this set, so we don't have this. And we will need to compare these this tag with the tag bits from the address. If they match, then potentially we already have our data in this cache. The only last thing we need to check is this valid bit. This valid is indication whether the information in this block is valid or it's garbage. Now, what is the case? Why the bytes here could be garbage? Well, that's because at the very beginning, you don't have anything valid in the cache yet before you retrieve a copy from the DRAM. So this valid bit will be set when the first time the cache trying to get a copy from DRAM and put it here. So if you access this particular block at the very first time, this will be an invalid. In that case, even though this tag matches, this is not the block that we want to access. So it's the garbage information. And that's called a cache miss. So the processor will then initiate the actual data transfer to load data from this DRAM somewhere here and load data into this block. Then set the tag, set the valid bit. Then the next time, if you use the same address, or not necessarily the same address, if you use this same set index and tag, you'll find that tag here, and that's valid already because you just loaded ahead of time. And in that case, you will find the data you're looking for in this block. And that's called a cache hit. So that's good news. So when you have a cache hit, you don't have to go further down to retrieve data from DRAM. So that was the workflow principle of operation of the cache, and the number of blocks in a set will determine whether it's a direct mapped, this is a direct mapped, or it's a set associative, or actually it's a full associative cache, but that's just a special case. So this direct mapped is where for each set, you only have 1 block. So you only have to compare with 1 tag. If you have more than 1 blocks, then you need to compare the tag from the address with every tag here. And that's going to take a little bit longer. But that will give you an opportunity to find a match if you can use the block that you already fetched to the cache.
Professor, I have a question.
Yes.
What kind of a question can we expect in the cache part of the exam? Like, will it be more towards, will you give us the addresses, and do we have to let you know what are the tag bits and what are the block bits, or what is the set index, or will it be like you'll give us multiple memory addresses and we have to calculate, like, will it be a hit or a miss for the next time? And how will it be? Could you please explain?
Yes, that's a very good question, and you already gave perfect answers. So those are all valid questions that I may have. So of course I cannot share exactly what I will have on the exam, but you can expect that I'll have some example addresses, and I'll ask you about the number of bits. How's that affect the structures here? Um, does that make sense?
Yes, that makes sense. Thank you, Professor.
Yeah. Yeah. So this is a summary of the cache parameters. So this is something you want to, look into, you know, find out, um, how these are defined and why do they have such relationship. For example, why is this number of tag bits comes from this? Okay. Memory models. We talked about the memory address, and also we give you some examples in the lecture. The way we use memory addresses using pointers, and the scope of the pointers. Um, we didn't talk about this endianness of the memory data organization. Little endian and big endian, those are very widely used terms. You want to read this a little bit. Really, these two terms are concerned about when you have a multi-byte data. Like say you have a word which has 2 bytes, or a double word has 4 bytes. How would you arrange these individual bytes in memory when you want to read or write this multi-byte data? Um, yeah, so this is the endianness. Stack is a memory region that's dynamically allocated, um, especially when you have a function call uh, in your program. In that function, um, when you enter the function call, a stack segment is allocated so that you can have your local variables allocated on the stack. And when your function returns, that stack segment will be that part of the um, um, fragments that you allocated on the stack will be returned. So it will release the memory back to the system, so you can make another function call. Um, right. So this is an example of subtle errors may arise as a result of misuse or misunderstanding of the stack. You can take a look at of this example. Um, to see why there's error, because this variable b is a local variable which is on the stack, so you should not access it um, outside this function, because when this function returns, the memory allocated will be reclaimed. So the if you use this as an address, then the um, the information that will be you try to access later on will actually already be released back to the system, back to the operating system. Um, you can read about memory protection units and dynamic memory allocation. We use malloc and free as a pair to dynamically allocate space in so-called a heap structure. And there's garbage collector that runs periodically to claim the fragments of the memory that are no longer referenced in the programs. Let's see. Memory model of C, this is something you should be familiar already. This just emphasize the scope of the variables, global variable, automatic variable, local variables. You can pass by value, pass by reference. I didn't talk about this in a lot of detail in the class, so you can use less time. All right, so that's the memory architecture. And so that's the 16 pages that I just went over very quickly. Because it's open book exam, and you don't have to memorize every single page on concepts or terms, but you should get familiar with the content and be able to refer to these concepts if you need it, and also understand the some reasoning behind it and some fundamentals of these memory architecture. And the video for this is here, post here in week 9, and it's just one lecture, one recording. All right, so then we'll go next to week 10. So week 10 is multitasking. Also in week 10, we talked about another part of AVR processor, the timer, and we'll talk about this at the very end today. Multitasking is covered in the textbook from chapter 11.1 through 11.2.4. So let me go to that. So we're talking about this first section and then this second section up to this point, 11.2.4. We briefly talk about these layers of abstractions. Really what in this section, we're talking about multitasking and threads and message passing. In this chapter, there are a few program segments, and I did cover many of them in the lectures. So you can go back to the textbook to read about this program example, try to understand what these functions do, and also by reading the text paragraphs. We talk about this imperative programs essentially is a sequence of operations. C is an example of imperative language. When you write a program, you assume that these functions will be executed one after another. Let's see. I didn't talk about this one, but it's good to just read through this if you can. Linked list is this sidebar here is just some background knowledge about the linked list, which is used in the example program. Linked list is a very commonly used data structure for storing a list of elements that can vary in length. So you can add an item in the linked list or remove item from the linked list. There's typical operations of adding new terms to the linked list or remove it. But that gets much more complicated when you have multitask or multi-threads trying to operate on a shared element. In this section, in the lecture, we spent a lot of time talking about threads. Threads are imperative programs that can run concurrently and share a memory space. So these are instances of imperative programs, and they share memory space, which means that the data, the variables, are the same variable, and that they will need to, um, coordinate their access to these shared variables. The reason we want to have these concurrent concurrent threads is to take advantage of their inherent parallelism, because some of the tasks can be done in parallel. There's no need to wait for another and executing a serial fashion. And this is oftentimes for performance benefits. But the downside or the challenge is how we can maintain the correctness of the program uh, while supporting this concurrency. First of all, we talked about how to create threads. We use standard API to do that. And the most commonly used ones are from this P threads or POSIX threads. And you can find P threads libraries for all the major operating systems, Windows, Mac OS, Linux, all of them support P threads. The creation is pretty straightforward. You want to have this thread function that you want to instantiate. So these are the imperative program. These are the sequential instructions you would like to execute within a thread. And of course, you can have different ones, but in this example, both threads use the same function. Okay? And the input arguments are passed in, and they choose to use default properties for the thread. This null pointer can be replaced with a pointer to a property structure. You can define some properties of the threads by not using the default ones. Thread ID is the identifier of the thread. Later, you can use these IDs to do pthread join, which essentially you wait for the completion of this thread, or you can do kill or some other operations using this thread ID. We need to join, so this API will not return. So in order to say this API will block until this thread completes. And when the thread completes, it will return the return status using this argument passed into this pthread join. So I think it's important that you read these shaded, these light blue boxes, because these are very good examples explaining to you what happens, and they have very detailed line numbers. You want to read through these to get an understanding about these examples. They give you very good information using this concrete example. And this example shows you what could be the error if you create a thread within a procedure like this, because the thread ID the argument to this routine is given by a pointer to a variable on the stack, which is this ID. And when this function returns, these variable will be reclaimed. So these pointer will become invalid at a later time while your thread is still running. The implementation of thread is talking about the underneath how operating systems support threads, the scheduler, which we didn't really talk about due to time limit, and the you know, and when the scheduler is invoked, the status of the thread suspended, resumed, so a different status change. Um, I think you can spend less time on this because I didn't really talk about this particular section. Okay, and this 11.2.3 mutual exclusion is used when there are certain segments of the program cannot be executed by more than one thread. And this case, we have to make sure, because there's situations that you want to, you don't want more than one thread to operate on some common variables or common program segments. You want to read this example? I think it's a good explanation why mutual exclusion is important. This is when you operate on the linked list, trying to add an item on the linked list, because the linked list has pointers, and it's very easy to corrupt this linked list if you have more than one thread that's trying to update the pointers. And this example explains that very clearly. So please read it. And this example illustrates a race condition. And that's one of the major reasons why we want mutual exclusion. And we will use a mutual exclusion lock, and that's often called mutex, for coordinate the access to the critical sections. So in this example, we have a solution to address the problem earlier, and by using this mutex. Similarly, update function has a similar issue, so there's some discussion here, so we want to read this. The very last section is deadlock. It's kind of a situation where you may have too many mutex locks. As a result, some of the threads are trying to wait for a clock that's occupied or locked by another one, which again in turn waits for the clock of this first thread. So if you have a thread that requires trying to acquire a lock while holding another lock, and that's a opportunity for this deadlock to happen. Let's see here. This is the example to talk about a perfect example of why deadlock happens. So you want to read this in conjunction with the earlier examples in figure 11.2. Okay, so for this chapter 11, you can read through up to here. We didn't talk about memory consistency models, so up to this page, it's fine. So that's multitasking. For the lectures, I have this 10A, 10B, and 10C. I basically segmented the whole lecture into smaller pieces that will help you to navigate more easily. So the first part is the POSIX thread, and then the challenges in thread programming, and then the message passing alternative and some theoretical foundations. So you can watch these lectures. But with that said, you can watch these lectures, but again, it's beneficial for you to read the text, read the textbook, those particular sections. That will give you more information and also give you a chance to think more, as opposed to just follow my lecture. I think you definitely need to read these sections by yourself. Okay. So I'm not gonna take a break. You feel free if you want to step away for a minute or two. That's fine, but I'll just keep going to cover all the points here. So we covered week 10, and the next topic is quantitative analysis. And so that's in chapter 16 of textbook. So it's here. And we're talking about, it's here, so 16.1 to 16.4. So it's from here to here. So about 20, 22, 23 pages. Now this seems a lot of pages, but you can, for example, we definitely covered this extreme case analysis, threshold analysis. We talk about the graphs, the control flow graph. We talk about basic block, control flow graphs, function calls. I'm talking about the things we covered in the lectures. So you can watch lectures and then come back to these chapters in the textbook. We talk about loop bounds, exponential path sequence, path feasibility, where we give an example of UAV control, where some of the path may not be feasible, and depends on the threshold. And we talk about execution time analysis, control flow, logic flow constraints. So if you, I would say for this chapter, maybe it's a good idea to first go to here. So that's week 12. Yeah, so maybe it's a good idea to watch these recorded lectures first. I broke down the whole lecture into basically 5 parts for this quantitative analysis. So A, B, C, D, E, and that is written here, but with the videos, for example, week 12, A, B, C, D, E. So that refers to these 5 videos. So you can watch these videos first, then go back to the textbook to try to review what we talked about in the lectures. I think in this chapter, the most important thing will be the control flow graph analysis. And also based on the control flow graph analysis, we use a model and to capture the constraints of these paths and solve that using integer linear programming. And that's one way to analyze the execution time. Let me go to that lecture, maybe bell. So we talk about the worst case execution time, and then we look at this modular exponentiation example, and then we turn that into a control flow graph. So here in each of the in the graph, each of this box is a basic block. The definition of basic block is, if you go into this block, no matter how many instructions you have here, there's only one exit point. So one entry point, one exit point. There's no other ways um, to get out, or there's no um, um, so you won't have any other branches in this block, within this basic block. And so using this control flow graph, we can capture the main basic blocks and how they are connected to each other, all the possible paths formed by these dependencies of among these basic blocks.
Excuse me, Professor, I had a quick question.
Yes.
So like for that chart, how would you go about finding how many different paths there are? I was looking at the homework and I was having trouble figuring out how to figure out the number of paths. So I thought I'd ask.
Right. So first, I think you can start with this basic block to understand, to draw these basic blocks. Then if you can group some of the instruction into the basic block as much as possible, then you will find that that's one basic block, and then you will only have, for example, this is a branch instruction, right? This is an if statement. So this instruction can go either true or false, right?
Yeah.
And after that, you have a bunch of other instructions. And as long as there's no other branch instructions, then you can group all these as one bigger basic block.
Okay.
Yeah, I think the key is to form these basic blocks where you don't have other branch instructions in the basic block. Then you will find these possible paths.
Okay, awesome. Thank you very much.
Yeah, you're welcome. And then on top of that, we will use the so-called program path analysis to find the longest path through the program and find loop bounds and etc. And this particular example is for demonstrate the path explanation, because this is a for loop. So essentially all the loop iteration will go through 100 times. And because we have an if statement here and we have if else, so based on the condition of this line here, we may either go this path or this path. So that's two possibilities. And each of the loop iteration has these two possibilities. And so altogether you have 2 times 2 times 2 for 100 times. And then that's 2 to the power of, actually not 100, this 10,000, because we have nested for loop. And how to determine loop bounds? Well, we will have to rely on the condition for ending the loop. For example, in this example, we have I is the exponential bits, and that's 32. So we know each loop iteration will decrement this I by 1. So that will give us 32 times. So that's the loop bound. We may not be able to find all the loop bounds. Depends on really the loop iteration variable and how it's given. And if it is not a constant number as we have here, then it's harder for us to determine the loop bounds. Okay, then we move on to use this example to illustrate how we solve integer linear programming to understand the worst case execution time. In this example, we have xi being the number of times a basic block is executed. So this is basic block 1, so it corresponds to x1. And similarly, we have x2, x3, x4. And then dj refers to the number of times the edge is executed. So we have D1, D2, D3, D4. This actually is a pointer back to here because this as a loop is possibly this condition checking is going to be executed for many times, and we use D4 to represent that this edge is going to be executed D4 times. So we'll have all these, and then from looking at the control flow structure, we'll come up with some constraints. For example, D1 equals X1 equals D1 equals D2, because there's no loop or anything branch. So if we go into D1, you will definitely execute this basic block for X1 times. So that's why we have D1 equals X1, similarly equals D2. And also we have constraints like X2 equals D2 plus D4. So let's look at that. X2 is how many times this basic block is executed. So that's going to be the same as D2 plus D4. Because D2 is how many times this edge is executed. Whenever you execute this edge, you will definitely execute B2. And D4 is this self-pointing arrow, and that's when you have another loop iteration when the loop has not ended. So D2 plus D4 is definitely equal to X2. So you can find similar other constraints, and our purpose is to maximize this C I times Xi. Ci is the upper bound on the time taken by this block, and so this B1, the time measured, the time taken by this B1 block times X1 will be the total time executed by this basic block. So we add them together. That will be the all the time, the time needed for executing all the basic blocks, and we try to maximize that, and that will be the worst case execution time. So we can solve this using integer linear programming, which is not an easy problem. It's MP hard, but there are software tools can help us to resolve that. There are some cases the branches have dependencies. So in this example, the climb underscore max is the threshold, but depends on that, only one of these branches will be executed. So that's one particular case we know we only will need to execute one of them. The worst case execution time compositionality. The main message here, if you know a task has two parts, A and B, and the execution time of A, the worst case execution time of A, and you know the worst case execution time of B. So can you say that for the task T, the worst case execution time will be the sum of these two? The conclusion here is that it's not always true, because you cannot simply compose these two together, because the task A and B may have some common variables, so both of them will depend on the value of that, and that will not always guarantee when A has the worst case execution time, B will have the worst case execution time. So it's not equal to the sum of these two. This is the part we talk about the effect of cache to program behavior. I think this is closely related to the very last homework. You want to pay attention to these several slides. What we're trying to say here is depends on how you access the variables which are stored in memory. you may or may not have benefit if you access the same variable the second time, given a cache hierarchy. In this example, we have a direct mapped cache which can hold 2 sets of data, and each set has 4 floating point numbers, and these 2 arrays are stored contiguously in memory starting at address 0. So when you have n is 2, so you're going to be reading x0 and x1 and y0 and y0 and y1 from the cache, and these 2 are packed together in one block. So it's beneficial that you have a cache hit, because when you load x, y is already loaded into the block. That's the kind of what we call spatial locality, which means that when you load x0 and x1, by the design, the cache loads the whole block, which consists of y0 and y1 already. So you already have y0 and y1 in this cache block. So as a result, when you try to access y0 and y1, they're already there in the cache, and that saves time on the program execution. If you don't have that, for example, if you have different number of bytes or different number of floating point or elements in these arrays, you may end up having, in this example, you end up having the caches keep being invalidated, because you have to move out the elements from X in order to accommodate the elements from Y. You didn't really take advantage of the cache organization in this case. So the execution time will be longer. It will not be benefited by the cache architecture. The very last part in the in the quantitative analysis is to measure the runtime. There are several things we do. We can put in some instrumentation code to sample the CPU cycle count, and also you can use simulators or logic analyzers. But in this lecture, we talked about how to use instrumentation code. There are some pitfalls you need to pay attention, because instrumentation incurs small overhead. So if you want to measure a tiny execution time of a few instructions or tens of instructions, the measurement may not be accurate, because the instrumentation code itself will consume some time, which will affect the measurement accuracy. In that case, you have to repeat the code that you want to measure for maybe tens or hundreds of times to make that execution time longer. When you add extra instrumentation code, the effect will be minimal. Also, for measurement, when you have multitasking, you will have to think about when the task may overlap, or some tasks may not be active. So the measurement may not accurately reflect the true ground truth. Also, there are factors of multi-cores and multi-threading. If the task is not locked, then the task will be moved from one core to another core. So the executing time will be actually longer, because there's movement, context switching between the cores. And also power management effect. If your CPU speed change based on the power consumption, power profile, the timer may get reset during hibernation, and when you use the CPU speed to calculate the time, then that number will be off if there's power management effect. So all these are covered in the textbook with some good examples. So I would like you to maybe watch these videos first, then go back and read the textbook. Each of these videos is around 20 minutes. Okay. All right, so getting next topic, this AVR processor. We talk about AVR processor in addition to the regular lectures based on the textbook. For AVR processors, I don't have a complete textbook chapter for those contents. All the contents are in these slides. And I talk about these several topics, I/O, timer, interrupt, in multiple weeks. But you can refer to the very last set of slides. So that's week 12B. So that's here. Okay. So this PDF has all the, I believe it's 28 slides that cover these three topics. So you can refer to the slides in this deck. For the videos, I broke it down to three pieces. So the first part is week 8B. So if you go back to week 8, you'll find one recording for talking about the I/O. And then in week 10, the video 10D talks about timer. And then we have the interrupt part in recording in the week 12F. So that's, yeah, I believe it's here. For the AVR process, I think, we had homework 3 was on this AVR processor. That was a good example how you should, program the processors through the registers. I think it's good enough, or I should say it's adequate if you can review all the examples that we talk about in the in these several videos, and that should be sufficient. Okay, very last part is about the lab 2 and lab 3. I don't expect to have a lot of questions from lab 2 and lab 3, but you can anticipate maybe one question from lab 2 and one question from lab 3. If you worked with your teammates on the lab assignments, I don't think you have any problem answering these questions. These questions will come from the design you had, hardware perspective and software perspective, or combination of both. So I think you just go back to review the lab reports that you submitted. If you did only one part of the lab, you should go review the whole lab reports to maybe ask your teammates to explain a little bit what you did on the other part. So that way you have a full understanding of the labs. All right. I think I covered all the contents I would like to talk about. Again, just to summarize, this is just a reference, a guideline for you to have a way to refer and to help you find the contents, navigate through the textbook, slides, and videos. If you attended all the lectures, I think you will have a good understanding about what we talk about, so you don't have to review all the videos again. You just need to read the textbook, go over these pages, familiarize yourself where you can find these important concepts. If you missed some of the lectures, then I highly encourage you to review the videos, watch them again, and then go back to read the corresponding sections in the textbook. I think I'll end my review here, I'll be I'll give you a chance to answer any questions that you may have. Any questions?
I have a small question. So the outline is kind of a little bit confusing. So is the final exam only going to be on topics from week 8 to week 12, or is it like all of it before the midterm exam as well?
So the topics that will be covered in the final exam will be all the contents that are listed here after the midterm. So these are all after the midterm. No questions will be on the topics before the midterm. Is that clear now?
Yep, that's clear. Thank you.
Okay, so if you don't have any other questions, I just want to make a comment about the grades. So far, I have all the grades back from the TA, and of course, we don't have the grades of the very last homework 4, which is due this coming Sunday. I would like all of you to submit by the end of Sunday, so we can have all the grades quickly, even be ready before the final, or somewhere maybe 1 day or 2 days after the final. I would not, I prefer not to give you late penalty for the homework 4. So just make effort to submit by the end of this Sunday, 11:59 p.m., so that we can have all the grades. The grades that you saw or you find in Blackboard, those are the raw grades. I think there's one column maybe showing the final or total. Don't count that. What's important is all the labs and homework, including the midterm, you have the raw grades reflected correctly in Blackboard. What I will do is I will pull the grades off from Blackboard into my own spreadsheet. Then I will do the final grade calculation because each item, homework or labs, they weigh differently. So I will do the final calculation on my own spreadsheet. So all the, other than the individual grades for labs and homeworks, the other columns in the Blackboard are not reliable. So don't fuzzy on those total score there. If you have questions regarding your individual grade, you can email me and I can respond, let you know what I have here on my spreadsheet. But again, so please submit your homework 4 by the end of this Sunday. So there's a question. Let's see. The exam is going to be 2 hours. And again, the exam time, I believe, is next Wednesday, starting at 6:30 p.m. And I do require you to log into this Zoom session and turn your camera on. If you have issue with your laptop, you should be prepared to call in from your smartphone with your camera turned on. We'll do the same thing as we did in the midterm. Myself and my TA will be online and monitoring the exam. I can respond to questions, and you will take the exam through Blackboard and submit through Blackboard. So it's the same one as we did in midterm. And for people who require accommodations, I will be able to provide that, given the same accommodation letter that I received from last time.